Hi everyone, my name is Brian, and I'll be talking about examination of RUM and RUB as potential chemotherapeutics. And RUM and RUB are two novel compounds developed here at AC, and we examined how they functioned as potential treatments for cancer. So first we have to define cancer, and cancer is really a family of diseases that all behave in similar ways and have really similar traits, and we call these traits the hallmarks of cancer. And the way that chemotherapeutics work is they target one or two of these traits in hope of disrupting the cancer and causing cell death or apoptosis. Chemotherapeutics have kind of several traits you want to look for, so they have to be selectively toxic, meaning that they kill more cancer cells than non-cancer cells. And this is really important because if it's killing a lot of healthy cells, that results in a lot of damage to the patient's healthy tissue and organs, along with the cancer. You would want it to be affordable and you want it to be soluble in body fluids. And this is important because as cancer can metastasize and spread throughout the body, you want your chemotherapeutic to also be able to spread and really fully eliminate as much of the cancer as possible. You want low resistance in cancer cells, meaning that because cancer cells divide so rapidly, they're always adapting. And so sometimes as you continually use a chemotherapeutic, the cancer cells adapt and become resistant. So really, if ideally you want low resistance in a chemotherapeutic. And because cancers are always kind of adapting, there is always a need for new chemotherapeutics. So that brings us to cisplatin. Cisplatin is a really popular chemotherapeutic developed in the 1980s. The structure is on the right. As you can see, it's a square planar uncharged molecule. And there are kind of a few issues with using cisplatin. Cancer cells can develop resistance. So once cisplatin actually enters the cell, those two chlorines detach and become ions. And cancer cells can actually pump out the platinum core with the nitrogen ligands. It's highly toxic to patients, so it does eliminate a lot of cancer cells, but also it's highly damaging to the patient's healthy cells. And the way it works is it halts DNA transcription and replication. So, as I mentioned before, the chlorines can detach from the platinum core, leaving two binding sites free on the platinum to be able to bind to the cell's DNA. And it can bind either in intra-strand or inter-strand crosslink. So intra-strand means both binding sites are on the same strand of DNA. And this can, when the strands of DNA separate and you have transcription or replication, the cisplatin physically blocks any of the enzymes from processing that strand of DNA, which can result in cell death or apoptosis. In an inter-strand crosslink, the strands of DNA actually aren't able to separate, and this can cause error-prone DNA repair, which can result in cell death or apoptosis. So that brings us to cisplatin and its predecessor or its successors or derivatives. So we have a second generation of compounds: oxaliplatin, carboplatin, and tetraplatin. All of them have platinum core with nitrogen ligands. Two have oxygen ligands as well, while the third has chlorine ligands. And while they can kill some cancer cells, we still need to do more research because some of them are actually have more severe side effects than cisplatin. So that leads us to 6 compounds developed by the Smucker lab here at Austin College. And again, you see the platinum core with the nitrogen ligands, but a unique feature of these compounds is that they also have a sulfur bond to the platinum core instead of chlorine or oxygen. And this is really important because we think that, or we hypothesize that the sulfur bond is more stable outside the cell and less stable inside the cell, meaning that it should be easier to transport throughout the body and more reactive once it gets in the cell. All 6 of these compounds were looked at by previous students. Only 2 were found to have any sort of toxicity, which were B1M and A2D. That brings us to the 2 newest compounds, RUM and RUB. RUM is on the left and RUB is on the right. And they were both named after the amount of rubionic acid ligands they have attached. RUB has 2 rubionic acid ligands, while RUM has 1. So the goals of this project were to look at all three drugs, B1M, RUM, and RUB, to see if there's any sort of decrease in viability in the cancer cells where there should be, because it wouldn't be effective chemotherapeutic otherwise. I wanted to also look at gamma H2 axon junk signaling to confirm nuclear binding of DNA. And this is important because these 2 proteins tell us if our compounds are actually damaging the DNA instead of something else, and that they function in a similar manner to cisplatin. And third, I wanted to treat the cells with B1M, RUM, and RUB in conjunction with DNA repair inhibitors. And so this was important because sometimes cancer cells can repair DNA damage faster than chemotherapeutics can cause and induce damage. So if you combine a repair inhibitor with the chemotherapeutic, you can potentially have a highly effective treatment for cancer. So first I'm going to go over the experiment, the data from the experiment you're going to be looking at today. All of the experiments are MTS assays. And so the basis of this is that cells are plated in a well and then incubated with the chemotherapeutic. Then after being incubating with the chemotherapeutic for a fixed amount of time, MTS reagent is added. And this causes a colorimetric change. And the more intense the colorimetric change, the more cells are in the plate. And so you'd expect if you treat with a chemotherapeutic, you have a less intense colorimetric change because the chemotherapeutic should have killed the cells. So all the data you're going to be looking at is MTS assay, and all the data I have gathered today is from cancer cells. So first we have Cyrene, and Cyrene was supposed to be an environmentally friendly alternative to a lot of organic solvents commonly used in synthesis. We'll go over why, maybe because it was easy to manufacture or environmentally friendly to manufacture, that it might not be safe. So you have saline, cisplatin and saline dissolved in saline, then you have Cyrene, then RUM dissolved in Cyrene, and then RUB dissolved in Cyrene. And so you can see saline doesn't really kill any cells. We wouldn't expect it to kill any cells. Viability hovers right around 100%. When cisplatin is incubated and with the cells, then you see decreases around 50% viability. And so we can tell cisplatin is doing what it's supposed to do, is killing cells. RUM and RUB both have lower viabilities than cisplatin. But the problem is Cyrene, which is even lower than the RUM and RUB in terms of viability. The problem here is this means that any decrease in viability compared to saline or cisplatin is really due to how toxic Cyrene is. So just because it's eco-friendly doesn't mean it's not toxic. And this meant we had to kind of change our solvents. And so we use DMF as our next solvent, which is a really common organic synthesis solvent, and the structure's on the left again. So again, we have saline, cisplatin and saline, DMF, B1M dissolved in DMF, RUM dissolved in DMF, and then RUB dissolved in DMF. And with both saline and DMF, you can see viability isn't really affected. Cisplatin, again, you see that 50% viability. B1M didn't really do anything. Again, hovers right at 100% in terms of viability. RUM, also 100%. RUB, maybe a slight decrease around 85, 90%. There was another issue when we used DMF. I noticed that a lot of the platinum compounds were actually falling out of solution. I could see the crystals on the bottom of the plate. And that means that because it's falling out of solution, it's not in the media, the cells can't actually interact with the compound. So we had to change the solvent again. And so we used DMSO, which was another really common organic solvent. And so the structures on the left, we have saline, cisplatin, DMSO, B1M, RUM, and RUB all dissolved. And then B1M, RUM, and RUB are all dissolved in DMSO. So again, saline doesn't really affect viability. Cisplatin, we see pretty low viability. DMSO, we do know is toxic to the cells, so there is a decrease in viability. B1M, you see a decrease in viability. RUM and RUB both appear to be pretty much ineffective, especially compared to DMSO. The error bars here are pretty large just because I have less replicates for this due to COVID-19 and campus being shut down and everything being shut down, the rest of the world. So that brings us to kind of, that's essentially what I have for AIM-1. A lot of RUM and RUB, even B1M, all seem less toxic compared to cisplatin, and that they do have solubility issues, which presents a challenge if we were to try to translate this and treat it to live animals and humans, how we would be able to effectively have them be transported into cells, because you can't treat people with a chemotherapeutic and an organic solvent because that would be highly damaging. And unfortunately, I didn't really get to AIMS 2 or 3 because, again, campus canceled, global pandemic, the whole 9 yards. So conclusions, styrene, highly toxic to cells. DMSO resulted in less crystallization than DMF upon dilution of the platinum compounds, which meant DMF, you could tell there was more accurate result, or DMSO, there was more accurate results. This crystallization could have resulted in inconsistencies in the data, especially with DMF. Selective toxicity can't be determined without data from non-cancer cells. So because all the data from my project is from cancer cells, I can't say these compounds kill more cancer cells than non-cancer cells. Also, wash your hands at social distance because I want to leave my house. And so future directions, I would want to finish MTS replicates for the cancer cells and non-cancer cells, and then do apoptosis assays for both sets of cells, because I want to confirm that any decreases in viability are due to the cells dying. I want to continue with AIMS 2 and 3 and examine junk and gamma H2AX expression, and then treatment with DNA inhibitors, and then combo treatment of RUM and RUB and the inhibitors. Hopefully I get to graduate, eat at a restaurant, go to the gym, sneeze in public without getting a dirty look. Here, I would like to acknowledge the Austin College Biology Department for giving me this opportunity, Tri Beta for giving me funding for this project, even though we didn't get through all of it because of COVID-19, the Discovery Foundation for funding, past and present Barton Lab members for all their support and data and setting up this project, all of my friends and family for their continual support, and then of course Dr. Barton for being my research mentor for the past 4 years. Here are my references, and that's the end, guys.